probability distributions in that if it added up to 1, it's a probability distribution, and if it doesn't add up to 1, it's not a probability distribution. Remember that? But now we're going to talk about different kinds of distributions. We have normal distributions, binomial distributions, and we're going to talk about geometric distributions. Okay? So these are the 3 different kinds that we're going to discuss. All 3 of them are probability distributions. Okay. All right, so normal distribution, again, there's extra videos that are explained differently than I explain it on page 121 in the statistics books, which is posted on Canvas. Yes, whole time I've been saying that. The whole book is on Canvas under modules. Okay, a distribution, guys, is a description of the possible values of a random variable and the possible occurrences. Okay, so when we talk about like drawing a card, we have 4 suits, probability of drawing a heart, a club, a spade, and a diamond. We would have a graph showing how likely we are to draw any one of those suits, and that would be the distribution. Okay, a normal distribution curve is recognized by its shape. It's also called a bell curve. Okay, so because its shape looks kind of like a bell, and the reason it has this shape is most of the data is located right around the center, which is the average. Grades typically follow a bell curve. In a normally distributed class, these are the C's. Okay, as you come this way, A's and F's. Most people get average grades. That's why a C is considered to be an average grade. So that's probably the bell curve you guys would be most familiar with seeing, would be like a normal distribution of student performance. Okay, normal distributions are symmetric. So both sides of the curve, if it's a true perfect normal distribution, both sides of the curve will be exactly the same. Completely symmetric. Now, in reality, real world data, a normal distribution is not going to be perfectly symmetrical most of the time, but it will be close. Okay, this one is obviously perfectly symmetrical, and as we can see, the majority of the data is in this like 68% range, so it would be 34% this way and 34% that way. That would be most of the people. If this was data about people, most of the people would be in this blue bit here. And you'd have less people, like over here you'd have 1 or 2 maybe. And you know, as you go, you get less and less people for whatever these categories are. They could be grades, you know, this would be like a 70%, 80, 90, 100. Or they could be income. Most people are here in the, let's just say, $30,000 to $50,000 range. And then you've got very few people over here in the $1 million range and very few people over here in the I don't make anything range. You know, so we have normal distributions. The actual, if you're talking about salary scale, the curve is skewed. It's going to be distributed. It's not going to be a true normal distribution because you're going to have more people over here than you do over here because more people are poor than are rich. Right? So, okay. So to remind you, a discrete variable, the discrete values are individual values. They can't blend into one another. An example of a discrete variable would be the number of cars in a lot. I can't have 1.68321 cars. I have 1 car, I have 2 cars, I have 3 cars. You don't have parts of cars running into each other, right? Continuous variables can be any integer, decimal, fraction, and the values could maybe blend into each other. So if you're talking about like volume of water in a swimming pool, that changes daily because of evaporation and the rain. And it's not like I instantly have 1 gallon in this pool, I instantly have 2 gallons, I instantly have 3, I instantly have 4, and then if it evaporates, it goes from 4 down to 3. It doesn't work that way. There's variations in between the volume. So the numbers blend into each other and gradually change. So when you think about discrete, just think about separate. Okay, so discrete is separate. And I don't know if I spelled that right, but separate. Looking at this set of graphs, one of them is continuous, one of them is discrete. What do you guys think, continuous or discrete? Yeah, continuous because it's a line, so we have infinite data points on this line. And this one? Discrete because they're individual points, they're not blending into each other. Makes more sense now? Yeah. Yeah, so when you have continuous, your data can run into each other, and when you have discrete, you have individual dots. Okay. Lillian, and she takes a survey of all the heights of all the students in high school. Now, these are not individual students' heights, these are the number of students at each height. Does that make sense?
Wait, say that again?
These are not individual students and how tall they are. These are, if this is like 5'7", then there's this many students that are that height. This many students that are this height, and whatever. So here she's prepared this histogram of the heights of the students, and it's probably ranged data. So it would be like, this bar might be like 4'5" to 4'10" or something, and so on and so forth. We want to know, is it normally distributed? Is it very easy test for normal distribution? Come in and draw a bell. Does this kind of look like a bell then? No, it doesn't look like a bell. If it was a bell, then the tall ones would be in the middle and they would gradually taper off down to each side. So then the answer to this is no, it is not normally distributed.
So when it's asking if it's normally...
If it was a normally distributed histogram...
That's what it's asking you to do, is draw that bell.
Yeah, and if it's a normally distributed histogram, it's going to look closer to that.
Gotcha.
Because then you can see there's like a curve. Yeah. Now, is it going to be perfect because it's real world data? It's not going to be a perfect symmetric bell, but it will be not like jagged or zigzaggy or straight across. It'll have those slopes. Does that make sense? Okay. All right, so let's check this one. Thomas did a survey, and his high school had 100 students. Is his data normally distributed? No. Because again, we don't have this bell thing happening, right? So you're going to have the tallest points in the middle. That's the most student. If this was normal, you'd have the most students at whatever this height in the middle is, and then you have gradually less getting shorter and gradually less being taller. So no, not a normal distribution.
Okay, so basically when it has that hill thing, it's a normal distribution?
Yeah, normal distribution is a bell curve. It's called a bell curve, and it's gonna always kind of be, like that shape, like that curve. Like I said, in a histogram, you're gonna have bars that are going gradually taller and then gradually shorter. Or even rapidly shorter and rapidly taller, but it's going to be pretty even on both sides. Okay. All right, here we have one where we're going to graph our data. We're going to count how many each there are. We're going to put it into a bar graph, and we're going to analyze the shape. And we're going to say, is this data normally distributed? Okay, so She posted a problem to her friends on Facebook, and her grade 12 math project was to measure the lifetimes of batteries used in different toys. And they told her how many hours their batteries usually lasted in a toy.
You have to arrange all those numbers?
Yeah, you had to put them in
That's a lot of
order.
numbers.
Yes, it is a lot of numbers, but you put them in order, which I did for you already. But it's in numerical order, so 41, 55, 56, 62, like that, okay? You want to list them in numerical order first. You're going to do a lot of that in statistics. Things need to be in numerical order in order to do different things like finding the mean and the mode and standard deviations and stuff. So just get used to the idea now you're going to have to rewrite list of numbers in order. Okay? So I've done it for you though. And then I put this piece of graph paper here, but it's not big enough for me to put an individual bar between 41 and 171. So I have to do ranged data. I'm going to make a histogram of ranges of hours. Okay? So if I look at this and I have 41 to 171. Why am I'm on clear? If I go 41 to 171, my range is 130. I have 130 numbers between those two numbers. That's my range. That's what range is. Range is the how far from the smallest to the largest number. Okay? So to find our range, we take the largest and we subtract the smallest, and you get your range. Okay? So I need this many squares to take up 130 different numbers. So what I did is I took that 130 and I counted how many blocks I have, and I have 23 blocks. 23. So 23 spaces that I can use. And that gave me a 5.6 answer. So I'm going to use 6 as my range. Each one of these bars or spaces will count for 6 numbers. So the first one will be 41 to 46.
The 23 is how many spaces are on the graph, right?
Yeah, how many spaces across the bottom of the graph. Then we have 47 to 52. And I'm going to stop recording and just fill this out really quickly. Each one being 6 spaces. Now that I have created the graph, do you have to write out every single data point on here? Probably not. You can skip a couple or something to do it, but you need to know the breakdown. Now, I have one number in the range between 41 and 46. I'm going to use the highlighter. Okay, one number in the range between 41 and 46. I have no numbers between 47 and 52. I have 2 numbers between 53 and 58. I have 2 numbers between 59 and 64. I have 2 numbers between 65 and 70. And that's just me counting. There's 2 right there between 65 and 70. I have 1 number between 71 and 76. I have 2 numbers between 77 and 82. Sorry, 3, 4. I have 3 numbers between 83 and 84. 2 numbers between 89 and 94. And then 1, 2, 3, 4, 5, 6. And then 1. And then 6 again. And then 2. I have 3 and 3. And then 2. And then 3. And then 1, 2, and the rest are 1s. Is this normally distributed? You think?
What, the same? Yeah.
The only thing that would make me say no is this gap in the middle.
So would it be yes or no?
It's going to be a yes.
Because the highest points are in the middle.
Yeah, here's why I say this, okay, guys? Look, this gap in the middle, if I had done a different range of numbers, the number that was right here would be in one of those two. Do you see what I mean? So it's the range that changes that and gives you that gap. If I had a range that was instead of 6, tens, if I had gone by tens, then that one would have been in probably the second one. It would have been absorbed, and then I wouldn't have a gap. Does that make sense? So that little gap right there, I'm not going to worry about. Overall, the general shape. Now, is it a perfect normal distribution? No. But it's an approximate normal distribution. Okay, and that's what we want to do, is we want to put that in there. It is an approximate normal distribution, which means it's not perfect, but it's close. It's the right general shape. Do we remember from a binomial experiment there are only two possible outcomes? And that's a success of what you were looking for or a failure? You know, if you're looking for heads, you either get heads or you don't. If you're looking for a club, you either got a club or you didn't. Okay? So only two possible outcomes. There are the probability.
So like you either get the card or you don't.
Yeah.
So for it to be independent, like you have to pull the card and then put it
Put
back.
it back, yeah. So, yeah, there can only be two possible outcomes, a success or a failure. So you either get the club or you don't get the club. The probability of success must be exactly the same. So the probability of pulling a club is 1 out of 14. So each trial you do, it's always going to be 1 out of 14 because you didn't like throw extra clubs in the deck or take extra one. Yeah, and it has to be with replacement. Each trial has to be independent. So you're conducting the same experiment over and over and over and over again, flipping coins, pulling out cards, rolling dice. And it has to be the same every time. You have a success or a failure, you roll the same number of dice, you have the same number of possible cards. If you're pulling cards out of a deck, you can't have the card you pulled out gone then when you make your second, because if the card's not put back, the probability changes on the second trial. So you always have to start with the same conditions every time. So full deck of cards, the same number of dice, the same number of coins. You can't have a loaded dice or, loaded coin, like two-headed coin or something. It has to be the same. Okay, so how do you determine if an experiment is binomial? Okay, so we look at this. If I take a coin flip, just for an example, I have only two outcomes. Heads or tails. Maybe heads or not heads. Okay, if I'm looking for heads. Okay, it's a head or it's not a head. There's nothing else that it can be. It's not going to be like landing on its side and standing straight up in the air and being like, I don't know, am I heads or tails? No, it's one or the other. Okay. The probability of a head, no matter how many times I flip the coin, is always 1/2. Right? At the 17th time I flip the coin, it's not going to suddenly change and be 1/4 or something. The probability will always be 1/2 to get heads. And then every flip is independent. Okay? I flip a coin this time, it does not affect the outcome of the next time I flip a coin. So far, okay? So that is binomial. Contrarily, if I want to pull a marble from a bag with 3 red, 5 blue, and 2 green. Okay, I have 3 possible outcomes. Red, blue, or green. Okay, so it's not just success and failure. I can get a red card, a blue card, or blue marble, or a green marble. Okay, the probabilities of a red is 3 out of, let's see, 8, 9, 10. Probability of a blue is 5 out of 10. And the probability of a green is 2 out of 10. So the probabilities aren't the same. So I have too many outcomes, I have different probabilities, and if the trial is independent or not depends. Do you put the marble back or do you keep it out? So you'd have to state that. Am I putting the marble back or am I taking it back out? So I'm just going to say independent, maybe. But we already lost binomial when we had more than one outcome. I could have gotten one of 3 different colors. So this is multinomial. Okay, and that's what we want to look at. You go through one at a time and say, how many outcomes are there? Okay, 2. Good. So far I'm okay. Then you go to, what is the probability of each outcome each time? Okay, that's the same every time, or it's not the same. As soon as you hit one where it's not, you know you don't have a binomial, and you don't have to keep going at that point. Does that make sense? Okay. This in the last chapter. We already did this. We were familiar with this. A is the number of successes. P is the probability of success. Q is the probability of failure. I forgot to put it in here. N is the number of trials or experiments. Okay. One of the reasons we study the binomial distributions is because it's discrete data and it gives us a nice normal distribution curve. Okay. And the more trials that we run, the closer we get to that perfectly normal curve. So, like I said, we just did this. What is the probability of rolling a 2 exactly 4 times when rolling a dice 10 times? Okay. Well, the probability of a 2, when you just roll it 1 time, is 1 out of 6, right? Because there's 1, 2, and 6 sides. So that's a 0.167, because we're rounding. Okay, so the probability that we will get exactly 4 of them is 10C4, because we have 10 times combination. We want four 2s. And then the probability of a 2 is 0.167, and we want 4 of them, so to the 4th. So what's the probability of not a 2? It was 8, I think it's 833, isn't it? I'll just double check myself, but. So it's 1 minus 0.167. Yeah, it's 833. Yeah. So not a P, or not a 2 rather, which is Q. It's Q. And then 10 minus 4. Well, 10 minus 4 is just 6. Okay. So then we have to get our, so I'm going to do 10 combination 4, and that's 210. 0.167 to the power of 4 is 0.0007777796. 0.833 to the power of 6 is 0.334095025. And then I'm going to multiply these 3 numbers together. And I get 0.05457, which is 5.5%. So I'd have a 5.5% chance of rolling a 2 exactly 4 out of 10 times. So not a huge chance of that happening. Now, four of these that we're going to do, okay? We have the probability of flipping a head. He's going to flip a coin, right? And we want to know probability of a head is 1/2. 1 out of 2. So the probability of not a head is also 1/2, right? This is P. This is Q. So far, okay? Now these are A. So we're going to do 4 different equations because we want to know when A is 0, A is 1, A is 2, and A is 3. And N, when we flip a coin 3 times, N is the number of flips. N is the number of trials. So far, okay? So our probability when x equals 0 is 3c0 times 0.5 to the 0 times 0.5 to the 3 minus 0, which is just 3. Okay. The combination 3, any combination of 0, 3c0, or even a permutation 0, 3p0 is understood to be 1. Okay, so that's just 1. And then 0.5 to the 0, anything to the exponent of 0 is 1. And then 0.5 to the 3 is 0.125. So when I multiply those together, I get 12.5%. Okay, and then the probability that we'll get exactly 1 head is 3c1, 0.5 to the 1, 0.5 to the 3 minus 1, which is 2. So I get 3. 3c1 is 3 times 0.5 times 0.25, which is 0.375, which gives me 37.5%. So the probability of getting 1 head is 37.5%. And then I can do the probability of 2 heads. So 3c2, 0.5 squared, 0.5 to the 3 minus 2, which is just 1. And I'm going to get 3 times 0.25 times 0.5, which is 0.375, which is 37.5%. And then finally, what's the probability of getting 3 heads? 3c3, 0.5 to the third, 0.5 to the 3 minus 3, which is 0. Oops, I wrote the wrong thing in. 12.5%. And if we look at this data, if I were to graph it, I have 1, 0, 1, 2, 3. And if this was 12.5%, 37.5%, 37.5%, 12.5%, what do I have? I have a normal distribution. So binomial experiments will give me normal distributions if I do all of the A's up to n. Does that make sense? So here we did all of the A's up to n. We went 0 through 3, and that gives us a nice bell curve. If n was 10 and we did all 10 of them, 0 through 10, I guess that's 11, we get the nice bell curve. Okay, next one, we're taking a multiple choice quiz. There are 10 questions, so we have 10 possible things. The probability of getting the correct answer is 1 out of 4 because there's 4 possible answer choices, right? A, B, C, D. So the probability of guessing correctly is 1 out of 4. 25% chance of guessing correctly on multiple choices, guys. Not good odds. We want to know what is the probability he'll pass the quiz. He needs a 6 or better. So he needs to get 6 right answers. And then the probability of not the right answer is 3 out of 4, which is 0.75. So he has a 0.70, his 75% chance of getting the wrong answer and a 25% chance of getting the right answer on any individual question. So we want to know what is the probability that he will guess 6 of these correctly and pass this quiz. Remember how I told you guys I don't play the lottery because I did the math? This is why I don't Christmas tree test. So I have 10C6 because we have 10 questions. We want 6 correct answers. I have 0.25 to the 6th. That's a correct answer. And 0.75 to the 4th because it's 10 minus 6. 10C6 is 210. And this is 0.00024. And then 0.3164. When I multiply those together, I have a 1.6% chance, or rather Mark has a 1.6% chance of passing this test.
So this is how we do it like on all the quizzes that we get. It's basically the probability of me passing.
Okay? So this is why you don't Christmas tree test. Not good odds. 1.6% chance? That's terrible. We've got a better chance of rain right this second. Okay, and then the same thing here. A coin is tossed 5 times. Find the probability of getting exactly 3 heads. N is 5. A is 3. My probability of a head is 1/2. My probability of not heads is 1/2. So probability that we get 3 of them, oops, I put my parenthesis in the wrong spot, is 5C3, 1/2 to the 3rd, 1/2 to the 5 minus 3. 5C3 is 10. 5.5 to the 3rd is 0.125. Yeah. But I'll show you how to do it in the calculator.
I don't have a calculator at home.
I'll show you how to do it on your computer calculator.
I think I know how to do it.
Okay? All right.
How do you it's 0.3125.
You move 2 spaces over.
Okay.
Yeah, always 2.
Okay. I think I understand it now.
Good. Homework.
Did you hand out the packets yet?
No, I have not handed out the package yet. I'm going to hand those out right now. Pages. I didn't number it. Hold on. I might have